The talk will be about estimating stock price correlation using Wikipedia. Now, about myself. Okay, maybe that's not exactly what I wanted to show you today. Yeah, that's more like it. So I'm a chief data scientist at Gnosis. We are a fintech company, and we are analyzing Twitter data for finance. I got my PhD 2 years ago in natural language processing and machine learning. And I'm very interested in how these two areas, so unstructured data and finance, come together. Actually, this talk is going to be about how we can combine or how we can understand the one domain with the aid of the other. More precisely, how can we use unstructured data and what is its relationship with traditional financial data. And the reason why I'm giving this talk is because there were quite some questions around, okay, so there's a lot of unstructured data, but is it actually useful? Can we really make use of it? Because unstructured data is noisy, it poses a lot of problems. Let's say that we have text, how can we get from text to numbers or time series that we actually know how to model? So this talk tries to explain a little bit what can be done, what is possible, and maybe set some future directions. Okay. So as I was telling you, financial data, traditionally, it's time series data. So you get your usual pricing data, and you are used to the time series, and you are going to make a prediction based on your past observations. Now, in addition to pricing data and to other time series that probably some of you are already looking at, there's quite a lot of unstructured data that people slowly start to be interested in. So it can be things like annual reports released by various companies, or some brokers might have a piece of research that they are publishing. You can have also conference call transcripts. You can have investor relations presentations, news, press releases, and, well, if you are Bloomberg, they probably have, well, sure they have in-house content. Now, okay, but what about unconventional data sets? So I don't know how many of you are familiar with data sets like Wikipedia, its structured version DBpedia, projects like Wikidata. Have some of you heard about them or used them? Not so much. One person, yay. Okay, oh, okay, sorry. 3 people, 4. 5. Okay, good. Right, so then I guess people who use them or people who've heard them, maybe let's have a small poll. Do you think that there is some potential for using these data sets in finance? 1, 2, 3. Okay. Well, I still have lots of convincing to do in this talk. Good. So, okay. Because during my PhD, I was working with unstructured data, and specifically, I was looking at data sets like Wikipedia, DBpedia. Maybe you know of an ontology that was humanly created called OpenPsych, and it's open source version OpenPsych. Then there's also BubbleNet. So there's really a lot of projects out there. Some of them are created based on people collaborating and writing about different topics of interest, like Wikipedia. There you have about 10 edits per second. And the English Wikipedia currently has over 5 million articles. So that's an average of 800 new articles per day, which is quite impressive. Now, how can we go from unstructured data to a more structured representation that we can actually make use of and well, hopefully build a model that's going to predict, well, the holy grail, tomorrow's price. So the structured views of Wikipedia. We can look at Wikipedia in two different ways, at least. So one way is to look at the Wikipedia article itself. And this Wikipedia article, we can build a vectorized representation out of the content of the article. Additionally to that, we can also look at Wikipedia as a graph. So now, if we want to build a representation of the Wikipedia article, an interesting project that was recently set up is called Tuvok. Now, I guess most of you know about the word Tuvok model. For those of you who don't know a lot about it or are not very familiar with it, this model was proposed by Nikolov and others back in 2013. And the main hypothesis that it was built upon, like a lot of other models, is the distributional hypothesis, which for linguists is very important. And it basically states that if you have words in a similar context, they are going to have similar meanings. This model is not really what we would call a deep learning model. It's shallow. It has only 2 layers in the network, as you can see from the image. Has only one hidden state. And the idea behind it is that it wants to learn vector representations which can predict nearby words, so which can predict the context. OK, so this is very nice, but if you want to compare not words in Wikipedia, but we want to compare Wikipedia articles, we need to go a bit further than that. So one idea, which is basically Wiki2Vec, is, well, we know how to generate context vectors for the words in the Wikipedia articles, but in a similar fashion, we can also create a context vector for the Wikipedia articles themselves. And let's say that these are topics. So that means that if you have, let's say, an abstract from an article saying Unilever is an Anglo-Dutch multinational consumer goods company, and Unilever is a link to the actual Unilever company, which represents a Wikipedia article. And additionally, you also have the multinational consumer goods company, which is again a link to some other Wikipedia article. Then what you would do is you would assign an ID to each of these links in your text, and thereby you are going to generate vectors not only for your words, but also for article IDs, if you want. OK, on the other hand, we have the Wikipedia graph. So I don't know how familiar you are with the Wikipedia structure, but you can essentially build 2 types of nodes. You can build nodes which represent the articles themselves, or you can also build nodes which represent the categories in Wikipedia. And these categories are basically labels that are assigned to each article and that tell you, OK, so for example, Unilever is part of the London Stock Exchange, so its category will be London Stock Exchange, or part of London Stock Exchange. OK, so now we established which are the nodes. Now, the directed edges, you can have several types of directed edges. So you can have what we've seen before, the hyperlinks from article to article. You can have info box links, again from article to article. You can have links from an article to a category, or you can also have links between these categories. So you can build quite a sizable graph out of the entire Wikipedia. Now, OK, so we have the graph. Now, what are we going to actually do with this graph? Well, 2 things we could do, for example. So let's say we do something very simple. We have our nodes in the graph, and we say, OK, 2 nodes are similar if the distance between them is they are very close together. Or we can also say, hey, why not apply random walk algorithms on our graph? So we can look at PageRank, and actually, more interestingly, a version of PageRank called personalized PageRank, which it basically uses the query to define how important is the vertex that I am looking at. And it's going to prefer vertices which are close to this query. OK, so now we know how to represent our data set. How are we going to use these kind of representations in order to see if they are useful for any type of financial task? So, OK, the analysis that came up was, let's look at the FTSE 100 index. And let's see what kind of information can we pull out of that. OK, so we took the FTSE 100 index companies. We knew sector, market capitalization, quite a lot of information, just out of Wikipedia. Then we also knew how to compute the similarity between two Wikipedia articles, which these two Wikipedia articles are basically the companies that I am interested in, part of the FTSE 100. We used GenSim, Word2Vec. This allowed us to build our Word2Vec model and the enhanced version Wiki2Vec, and also to compute the similarity between any two articles. So we would obtain a pairwise similarity, something like this. So we would have company 1 and company 2, and its Word2Vec similarity. Now, there are several reasons why you're not going to obtain a similarity for each pair of two companies. The reasons may be your article is very short. There's not enough information in there. Or you are going, when building your Word2Vec model, you are going to set quite some thresholds in order to obtain something meaningful. And there's a reason why we are going to have missing values in our data set. On the other hand, we are going to have our pricing data. So this is your usual time series data set. And what we are going to do with our pricing data is that we are going to obtain our daily returns for each FTSE 100 company. And we are going to also compute a correlation for each possible pair. So again, like in the previous example, we have company 1 and company 2 and our correlation. And now we have two different views. We have, on one hand, our Wikipedia similarities, and on the other hand, we have our correlations from our pricing data. Great. So the question is, does the Wikipedia similarity explain correlation of returns? What is your guess? And why is that? What is the reason for which it does? You will say yes, because otherwise I wouldn't be here presenting in front of you.
They're in similar interest rates. Was it rhetorical?
Yeah, I was asking you. I was asking the audience. What is your gut feeling? Why is it really that? Because there were a few people who said yes, there is some correlation. Any idea why? Why should there be any correlation? On one hand, we have this unstructured data set. It has nothing to do with finance. Nobody ever came up with the idea of putting information in there that's actually, yeah?
There could be some sector similarity, for example, that to uncover the Wikipedia description.
Yeah.
In similar sectors, they might move in similar ways.
Yeah, we also thought so. But then you would expect that if you would pull a sector out, you're going to have no correlation whatsoever. Or you're going to have only correlation in that particular sector. Yeah? OK?
How do you take out the fact that they're all in the FTSE 100?
Sorry, again?
How do you take out the fact they're all in the FTSE 100?
How do I check that they are all in the FTSE?
How do you take out the fact? It's a confounding fact. It's a confounding factor.
It's a confounding. I didn't really think of that. What exactly would you mean that?
Well, it would be both in your Wikipedia aspect, that they are in the FTSE 100, people linking things along,
Right.
and their price moves will all be dependent. With lots of index flows, and they move the FTSE 100.
Yeah.
So it's something that affects both sides.
Yeah. That is an interesting observation. We did observe this in a very specific case I'm going to refer to. If you bear with me until the end of the presentation. So, okay. So there you go. Now this is the results that I'm showing here are for a subset of the FTSE 100 companies which have a market capitalization greater than 7, which is a median market capitalization among the FTSE 100 companies. The reason that we chose this is because if we take companies that have lower market capitalization, they do not have so much content in Wikipedia. Additionally to that, these companies, they have lots of content that is not particularly useful in order to determine how similar they are. So for example, they will have things like there is some conflict, there is some change in ownership, there is some restructuring going on, and that is very, very detailed in Wikipedia, but doesn't really help us with determining the similarity between this particular company and another company. So yeah, what we found is that it's not really the case that this is valid for a particular sector. It's more the case that it's valid above a certain market capitalization. Moreover, if we go even further and look at an even higher market capitalization, then the R2 becomes quite interesting. Now, let me come back to the question that we had previously. So before I was telling you about graphs and how we can use them in order to analyze Wikipedia data. Now what happens is that the graph-based similarity, it does capture exactly that you have information about companies in a single topic. They are part of the same topic, which is all of them are part of the FTSE 100. So all of them are going to be labeled with categories that are companies based in London, companies that are part of the London Stock Exchange, companies that are part of the FTSE 100. And that is going to imply that these companies are going to have they are going to be very similar based on the graph measure of similarity. However, this is not the case if we are using the word Tuvok model, because there the context is able to capture much more information, and therefore it allows us to see this kind of correlation, which we did not see with the graph-based measure. So yeah, it is, in effect, Wikipedia, an unconventional source of unstructured data, has explanatory power for financial variables. The other thing that we saw was that context-based similarity, so the word-to-back model is powerful enough in order to capture information within the context. But aside from that, nobody would have said there is any kind of information that we can pull out of such an unstructured source that nobody had an idea of using it for this particular purpose. So the hypothesis is that a lot more can be gained from industry-specific documents. So if we are looking at annual reports on conference call transcripts, there's much more information there because these data sets are created specifically with the purpose of financial analysis. Now, there are several applications that we can look at. So, yeah, why are we doing this? Why is it interesting to find such correlations? Well, one possible application is predicting financial figures solely based on unstructured data, or even thinking of a hybrid model that combines unstructured and structured data. Another possible application domain, estimating financial figures, ratios, statistical moments, other kind of relevant quantitative data which is not available. And one example is the time preceding the IPO. Here are some of the resources that I've used in the presentation. So for the Word2Vec and Wiki2Vec models, the Graphbased Similarity, and also I will make the notebooks of the presentation available in case you want to play around with it. So thank you. And if you have any questions.
Did you play with different time spans in the correlation of financial data?
Mm-hmm.
And which are the better best ones?
So different time spans. The data that I was showing, if we go back, starts 2013. Now, the thing is that if we look at, let's say, starting 2000 or even earlier, we are going to have the problem that that Wikipedia doesn't. In Wikipedia, the information gets captured in a different way than in a pricing data. So, for example, what happens when companies merge? You had the case of Siemens, which sold its an entire part of the industry to a different company. That's something that is very easily reflected in the price, but on the other hand, all these kind of changes are very hard to track in Wikipedia. So yeah, we did play with time, and the thing is that the more you go back in time, the harder it is to have any kind of relationship. Yeah.
Hi.
Hi.
I was wondering about how you did similarity between articles, because Word2Vec, you feed him sentences, and then it gives you associations with context. And so typically for each word, you'll get a vector which represents it in this new space, in this small space. So, but when you compare articles, there are many words in an article, and sometimes articles are not at the same, don't have the same number of words. So from just a vector for words, how do you compact them to compare articles?
Okay, so several observations here. Word2Vec is a collection of algorithms. There's the initial Word2Vec. What it did is you have one single word, and for each word you obtain a vector representation. And that vector representation is going to be finite. So that's why you can compare two words among each other. Now, the trick, let's say, that we applied in order to obtain the Wikipedia article comparison was that we were changing in text the link to an article with an ID that uniquely identified that particular article. So then this ID becomes actually a word in text. And therefore, we could obtain a similar vector representation for the for words, of course, and then also for this additional article represented by the ID. And because we have it in our, if you want, key, so it is among our keys, we can then retrieve it and compare the two articles. We could also compare an article with a word, for example.
So essentially, you reduced articles to like a bunch of keywords, and if the keywords were similar in a Word2Vec sense, then they were similar in an article-to-article sense.
Exactly like that. Yeah.
Thank you.
Thanks for the very interesting talk, first of all. And so thinking intuitively, if two companies are similar, right, according to Word2Vec or the graph, then intuitively there could be non-monotonic relationships between their stock prices. As in, assuming they're in the same sector, if the sector as a whole is growing, then there will be positive correlation between the stock prices. If the sector itself is not growing that much, then the two companies are basically competitors, right? So in theory, if one rises, the other should lose out. Did you consider that in the model?
Again, all these kind of observations that you can easily get from price analysis are very hard to obtain from text, unless, or at least you are not going to be able to obtain it out of Wikipedia. This is the reason why probably a hybrid model that combines the two is going to be more powerful. Because in the end, they are complementary data sets. You are going to obtain some information from your price data, but it can very well be that you don't have this price data available. Or let's say that the price data, everybody is using this price data, and everybody is running their model. So there's very little that you can gain in comparison to your competitor. But then, maybe if you are using unstructured data, whereas your competitor is not using it, there might be something in there that should not be overlooked.
Did you have a go
sorry.
Did you ever go at doing any kind of quantitative backtesting on this? So it looks like statistical arbitrage, effectively, if you're able to track what the movement between stocks of different companies is. So did you do any backtesting, and would you have made any money?
I think this is more like a let's try see what comes out of it idea. It's the reasonable answer to the question, is there any kind of relationship between Wikipedia and stock price data, is no. There shouldn't. Why should there be? Because Wikipedia itself cannot explain. And again, if you go back and you start looking at your data since, I don't know, the 1920s, there has been so much development in there. Maybe Wikipedia doesn't even track that information. Now, to backtest it, in what kind of setting? How would you backtest it?
Well, you could look at Wikipedia articles over the last 10 years, run the model on older versions of older iterations of Wikipedia, and work out what you would have decided to do, and track it against the stock price, and work out whether your statistical arbitrage would have worked or not.
The problem is that Wikipedia, as it evolves over time, doesn't really evolve in order to reflect price evolution, because it evolves very organically by people adding more information in there.
But it's just the similarity between two organizations you're interested in, and if they're moving in opposite directions when your model said they should be moving in the same, or one has moved because, I know, Pepsi results have come out but Coke's haven't.
It's very hard to get this kind of two companies moving in different directions, or these companies are competitors, these companies work in the same sector, out of Wikipedia. They will be similar if they are in the same sector. Again, if they are competitors, share the same sector, they will also be similar, because, I don't know, they are both tire manufacturers. So there are certain limits of what you can explain using this kind of data set.
Thanks.
Potentially, I think this is just could be the prelude of a statistical arbitrage strategy, because it tells you what the pairs you should be looking at, but then the next step would be, okay, at which point does the spread between those pairs that the model has predicted is too much out of line for you to say sell, buy, and so on. So that's what could be useful if it's reliable.
Hi, thanks for the talk. How do you combine the two distance metrics that you have? So you have one, the graph-based distance metrics between two companies, and one which is like the modified doc-to-vec, let's say, distance metric. How do you combine them? Is it a linear combination, or you have a non-linear function that's combining them?
Okay, so we tried using both independently, not combining them. The problem with the graph metric is that it does not really reflect similarity between companies. And the reason is because these companies, because I'm focusing on this particular domain, all of them are going to be highly interlinked, especially because of the categories. These categories are extremely high level. So as I said, the examples are all companies listed on the London Stock Exchange, where, surprise, all of them are. All companies in the FTSE 100 index. So because of this, I'm going to obtain, for all my companies, high similarity measures. And this is not going to help me to distinguish I don't know, if I have a pair Tesco and Sainsbury's, which are similar, versus Tesco and, I don't know, 3i, which are probably have very little in common. So in the end, the analysis was done on word2vec, which turned out to be much more powerful in getting exactly this kind of information out based on the context. An interesting question would be, why isn't the graph measure capable of extracting? Because usually these graph measures, they are very, people obtain very good results using graph measures for tasks like word sense disambiguation, where you have words from different topics and then see, okay, is this word, does this reflect topic A or topic B? Now, because I'm narrowing down, it seems that the same algorithms that work in a particular domain don't work so well in this particular example. But we haven't really dug into why and how to adapt this metric in order to be able to capture similarity within the domain.
Thanks. Okay, if there are no more questions, thank you very much, Dr. Delia Rusu.